is CORDIScovery. Hello and welcome to this episode of CORDIScovery with me, Abigail Acton. We are living in a dynamic landscape of threats, but AI, innovative thinking, and research funding are identifying some of the risks that are out there and how to tackle them. A better understanding of asteroids to improve our planetary defense systems, finding out what contributes to wild megafires to improve our risk assessments, and developing accurate small sensors that can detect and identify liquid chemical hazards at low concentrations. Today's guests have used EU research funding to develop innovative approaches to improve safety. Today, we will be hearing from Patrick Michel, who is a director of research at CNRS at the Côte d'Azur Observatory in Nice. He is involved in space missions to asteroids for both scientific and planetary defense purposes. He is the principal investigator of the European Space Agency's Hera mission, which contributes to the first asteroid deflection test through NASA's DART mission. Welcome, Patrick.
Hello, very happy to be with you today.
And we're delighted you're here. Emilio Chuvieco is Professor of Geography, Director of Environmental Ethics Chair at the University of Alcalá in Spain, and an elected member of the Spanish Academy of Sciences. His main interest is the use of Earth observation data to monitor environmental problems, particularly forest fires. Welcome, Emilio.
Hello, thank you, Abigail. Nice to be here with you.
Yeah, good to have you. Thomas Rinzavicius is a senior researcher in the Department of Health Technology at the Technical University of Denmark. He focuses on the application of nanomaterials for sensing applications, which can detect trace amounts of explosives, toxic industrial chemicals, as well as chemical warfare agents. Welcome, Thomas.
Hello, pleased to be here.
Thank you for coming. So, Patrick, I'm going to turn to you first. Whether for planetary defense or resource missions, we need to improve our understanding of the nature of asteroids, which is where the NEO-MAPP project steps in. When we think of asteroids, we might think of planetary defenses and just what an impact meant for the dinosaurs. But ongoing research has more dimensions. So can you tell us what drew you to study these small and hopefully distant bodies?
Yeah, absolutely. So in fact, asteroids are fascinating for many reasons. The first is that they are the remnants of the bricks that form the planet. They are now mostly between Mars and Jupiter in a belt called the asteroid belt. And contrary to planets which are big and are like cakes, they are very small. So in a planet, the material has been transformed chemically because it has been heated, like when we took the ingredients in a bowl and cooked them to make a cake. And asteroids are small enough that they record the original composition of the ingredient that formed the planet. So they are the best tracer of the solar system history, and they even may have contributed to life on Earth. And they are also fascinating because they are, most of them, very small, and therefore they have a very low gravity, and their behavior is therefore very different than the behavior of the material on Earth in the strong Earth gravity. And this is really challenging, and I love challenges. That's why I study them, because and we need to study them because this is a way to better understand how we can prevent an asteroid impact. If we want to deflect an asteroid, we need to understand its response to the impact, and also to advance in our knowledge of the solar system history. And the challenge is really to understand how they respond to an external action. Previous missions showed us their incredible diversity. Each time we saw an image of a new asteroid, we jumped on our seats because they are not at all what we were expecting, which show that we are still not really understanding them well. And therefore, these are the challenges we have to tackle, which is how to better understand how they respond to an external action in order to deflect it, or simply to understand how they behave against the process they experience over their lifetime.
Yeah, that's wonderful. Thank you. Super explanation. And also, of course, the composition is fascinating too. Lovely. So first of all, perhaps you could tell us why it was called NEO-MAPP. Let's get that out of the way. And then maybe can you tell us what work the project did to better understand the character, the nature, the movement, the response to external stimuli of the asteroids?
Yeah, so our project is called NEO-MAPP, for Near-Earth Object Modeling and Payload for Protection. Because in fact, in the project, we address two domain. One is to make great advances in our capabilities, in particular to model better how they respond to an impact, for instance, or to another external action. And the other area is to advance in a technology development and data analysis tools for space missions to asteroids, so that we can better analyze the data that provide the knowledge and also are used to validate the numerical models at the real scale. And one of the challenges, for instance, was to really understand how they respond to an impact, because in 2019, just before we started the project, we had a Japanese mission called Hayabusa 2 that made a small impact on an asteroid, and the crater that was produced by this impact was much larger than the one we predicted with our impact models.
Can you give us some numbers? So, I mean, for example, when you say a small impact on a large crater, go on. I actually know the answer to this, which is why I know the listeners are going to love it. Go on, tell us. How small, how big?
Yeah, absolutely. So, in fact, the projectile was 2 kilograms, launched at 2 kilometers per second, and we expected a crater of 2 meters. And in fact, the crater was 17, almost 20 meters in size, so 10 times more.
Goodness.
So we were completely wrong. And this is where we realized that our models are not able to capture correctly a process under the low gravity environment of an asteroid. In particular, when you make a crater on Earth, the event takes about a few seconds to take place. In low gravity, everything is slower, meaning that when you make a crater, it takes minutes to hours to develop. And this is very hard to capture in numerical models. So thanks to this project, we could develop new approaches to tackle this problem, and we were eventually able to reproduce the crater. Another area was to be able to develop technology that allow us to land on a small asteroid. Because, asteroids are very small. They have a small attraction. So if you land too quickly, you may bounce and go away. Like, on an asteroid, if I get excited on my chair, like when I'm speaking with you, I'm already in orbit.
Yeah.
Because they are very low, they don't attract well.
There's nothing holding you there.
Exactly. So we have to develop technologies that allow us to come slowly and make sure we stay on the surface. And all these are very challenging, and it's exciting because we have in a project different communities working together, engineers from industries and scientists, and it's always, a good thing to work together.
Yeah, no, it sounds like an excellent melting pot. And I remember, I think in a previous conversation we had, you were mentioning something about the images of an asteroid looking misleading, basically, leading you to believe that there were certain characteristics that in reality were completely different. Could you tell us a little bit more about that? Because I love that story.
Yeah, in fact, the thing is, the engineer, they have to start with assumptions in order to define the operation strategy when you get on an asteroid. And in fact, we don't know much about them because from the Earth, we just receive a faint light that comes from their surface. So, for instance, when we did past missions like Hayabusa 2 by the Japanese agency and OSIRIS-REx by NASA, we told the engineers, when we land on the target asteroid, don't worry, we'll have large areas without boulders. And in fact, when we arrived, there were boulders everywhere. So this is funny because when it happens, the scientists are super excited because we like to be wrong. We are always happy, by the way, because when we are wrong, we have new challenges. And when we are right, we predict it correctly, right?
Yeah, perfect. Win-win.
Exactly. But the engineers looked at us and say, hey, guys, you gave us wrong assumption. Now, how are we going to land with so many boulders? So this is interesting because they have to be very flexible and be able to revise entirely their strategy of operations when they get to these new worlds, because each time it's a surprise.
In real time. Yeah. And what did you find with the boulders?
So in fact, what we found is that there are basically no areas to land which are larger than 10 meters, while we said we would find spaces of 50 meters. So can you imagine that they had to command a spacecraft at 300 million kilometers from Earth, so 1,000 times the distance between the Earth and the Moon, in order to be able to land in a 10-meter space, which is absolutely incredible.
Yeah, no, that's absolutely amazing. And I'm going to steal your punchline. If I remember correctly, the boulders weren't boulders.
Yeah, exactly. So this is the thing, is that the response of these bodies to an external action cannot be predicted well so far just by images, because with these missions, we stayed about 2 years around an asteroid. We have a lot of images. We see many boulders, and yet when we touch them, we feel no reaction. Like if we go in a fluid or in a cohesionless sand.
Or like mist.
Exactly, like mist, exactly. And this, we could not really predict it just from images. So the conclusion and the lessons learned is that, at least for now, we need to have a direct interaction in order to determine the mechanical response of an asteroid, which is very important for deflection, for instance.
If we ever need it for planetary defense.
Absolutely.
Wonderful. Well, this is all really fascinating. Thank you so much for explaining it so clearly. And how will some of the innovations and some of the findings of your project be applied in forthcoming missions, Patrick?
Yeah, in fact, we are very lucky because we can immediately apply what we did in this project, because we already used it for the DART mission that impacted on an asteroid. And now we launched the Hera mission by the European Space Agency that is going to reach this asteroid again in 2026. And all the tools we developed, some of the instruments are on board this mission. So we are really in the way of using them. In particular, there was a flyby of Mars recently on March 12th, and all the data we get from these images of Mars and its moon Deimos will be using our analysis tools. And then we have another mission in development thanks to this project, which is called the Ramses mission, still at the European Space Agency in the Space Safety Program, that targets an asteroid called Apophis that will come very close to the Earth with no danger at all, but just a great opportunity on Friday, April the 13th, 2029, and we're going to visit them. Yeah.
Oh, lovely, lovely. Friday the 13th, yay. Well, we'll hold you to what you just said about it being no danger at all. No, I'm sure all the calculations show that. Thank you so much, Patrick. That was beautifully explained. Wonderful. Does anyone have any questions for Patrick? Yes, Thomas.
Yeah, thank you. So I'm outside your field, Patrick, so I'm sorry if I'm being too simplistic. I'm just curious, do we have now any viable technology or system to actually deflect asteroids?
Yeah, absolutely. We have at least a technology that was demonstrated in real with a DART mission that showed that we are able to basically send a spacecraft at very high speed, 6 kilometers per second, on an asteroid for which we only know the size initially and not even the shape, autonomously so that it hits it. And that was successful. The DART spacecraft, 580 kilograms, impacted at 6 kilometers per second a very small asteroid, only 150 meters in size, successfully. And the goal of the Hera mission is to be the sort of a detective that go back to the impact scene in order to tell us what exactly happened. But at least the technology to hit at high speed an asteroid was demonstrated. Of course, we need to develop other technology because one technique may be efficient for some cases, other techniques may be more efficient in other cases. So it's just a starting point, but it's already very nice that the first test was successful.
That's wonderful. It's like cosmic billiard balls, cosmic snooker. Excellent. I'm always amazed by the precision. I just find that phenomenal as someone who has problems reverse parking into a garage. I'm really impressed by the precision. Okay, I'm going to turn to Emilio now. Emilio, wildfires have been in the news recently and occurrences look likely to rise given changes in land use and climate. The Fire EU Risk Project brought together researchers, planners and responders to find a way to assess and manage the risk of megafires. So we know that climate change is going to make for more extreme weather patterns. Can you tell us a little bit about what the experts are thinking regarding the risk of what you call megafires going forward, please, Emilio?
Well, yeah, we have been observing in the last years that the total burn area is not increasing globally, but the extreme fires are increasing, and it's obviously related to the climatic and socioeconomic changes that we are observing, particularly those factors that lead to extreme fire behavior, heat waves, strong winds, very dry vegetation, and this is why we are finding accidents, casualties that are considerably important in terms of societal and ecological impacts.
Yeah. And we can clearly understand the impact of the climate. But when you talk about socioeconomic factors, what are you considering there when it comes to risk?
Well, the changes in land use, particularly in rural areas, are having important impact on fires because previously there were population working on the rural areas, doing, for instance, extensive grazing. And nowadays, most of these people are aging There has been a strong abandon on areas, particularly in Europe, and therefore the landscape tend to be more homogeneous. And whenever you have a fire, it tends to propagate much more continuously than in the past.
Yeah, that's interesting. Right. Okay. Yes, I wasn't thinking of that when we were thinking of land use. I suppose I was imagining something else, but I see what you mean. People aren't husbanding the natural resources as they used to, and it's changing the profile. Yeah, yes. I get you. Super. Okay, so what did Fire EU Risk want to do?
Yeah, we have a very large consortium of very different experts coming from different countries, and we want to analyze fire risk in an integrated way, considering not just meteorological data, which is what is mostly common by current fire risk assessment system, but also other aspects related to vegetation, as I said, characteristics, but also human activities, ecological values, ecosystem services, people preparedness for fire. So we aim to develop a holistic analysis or integrated analysis of fire risk conditions in different European areas. Previously, fires were mostly a Mediterranean problem, but nowadays we face also fire issues in Central Europe and Northern Europe. And also we aim to better understand how fire trends would evolve in the future, considering again climatic and socioeconomic changes.
Wonderful, excellent. And I know that you've been using Earth observation data as well to give you some clearer ideas. What is the Earth observation data showing you? What is that used for?
Yeah, well, actually, that's my main specialty. But we do is doing a periodic observation of fuel conditions in terms of both fuel abundance, meaning the amount of vegetation that is able to be burned, but also the moisture content, which is very important in terms of flammability and also behavior. Also, we use satellite data to improve, let's say, updates our current maps of wild and urban interfaces. Those are the most important in terms of high risk.
Wonderful. Okay, so when you say the fuel abundance, I get you can tell from the satellite imagery what's growing there. But what did you mean about moisture content? How is satellite imagery telling you about the moisture of those plants down on the Earth?
Yeah, well, actually, water absorbs part of the electromagnetic radiation that comes from the sun and is reflected to the satellite. Also, the thermal contrast between air and surface temperature is an indicator of moisture content and water stress.
Yes, so you can see where things are drying out and therefore obviously becoming more susceptible. So wonderful. This is the kind of data you collected and the people that were involved in that. But what were you actually, what tools did you develop? Did you develop anything that actually can be useful in keeping people safer and analyzing the risk of potential fires now?
Yeah, we hope so, of course.
Yeah, we all hope that.
We are very interested to help society to reduce the problems of fires. Keep in mind that we have extreme fires in the last years with a lot of casualties. I mean, recently in California, also Hawaii, Chile, etc., more than 100 people died as a result of fires. So we aim to develop a more holistic, integrated approach to risk, to fire risk, considering different conditions that are not very commonly considered in the current fire risk assessment systems, particularly the vulnerability aspects, the exposition of humans to fire, and also we aim to better understand how these extreme fires propagate, how the people can be better aware of the risk related to fire. I think it's important to notice that in many fire-prone areas, local citizens are not very aware of what they should do in case of having fire. I remember in Japan, I visited Japan a few years ago, and everybody knows what to do in case of earthquake, but that's not the case in fire-prone areas in the Mediterranean. That's part of the issue,
Right.
For instance, in 2017, more than 60 people died trying to escape fire. Probably if they would have stayed in their places, there would be much less casualties. So I think we need to inform also the population what to do in case.
Right. And do you have you developed any kind of early warning tools or any mechanisms to assist those who must perhaps launch evacuations or any tools at all?
Well, yes. As I said, most of the current systems are based on meteorological data, which obviously are very important in terms of fire, particularly wind, with humidity and temperature, but also we have added to those aspects other social aspects, ecological ecosystem services, etc. So we tend to have a more comprehensive evaluation of risk that would facilitate better, more objective criteria in terms of fire suppression. And we have put more emphasis on prevention than suppression, which has traditionally led the fire risk operational system.
Because I know you've also been considering sort of traditional use of the land. And of course, fires have always been with us. So I like this idea that you're not actually focusing that much on suppression, but it's more about management of risk, isn't it?
Yes. Actually, fire is a natural process. There are a lot of vegetation that is adapted to fire. And I think we need to live with fires and trying to use fires in a more efficient way, avoiding the negative impacts, but not suppressing at all, because at the end of the day, when you suppress small fires, you may have large ones in a longer period, and therefore they could be more extreme than they used to.
Okay, that's excellent. Thank you. Very, very clear. Okay, super. So a better, broader, more accurate picture that gives the people who are charged with keeping people safe a clearer idea of what the risks are and how to get out of a situation if it evolves. Super. Thank you so much. Does anyone have any questions at all? Yes, Patrick, please.
Yeah, I mean, this is very interesting. I have a question about, so you look at the conditions that may trigger fire, but are the fires mostly voluntary or accidents?
Well, both actually. I mean, human aspects are very important in fighting ignition and propagation. I mean, humans are both a factor of fire occurrence, but also they are affected by fires, of course. So in Europe, for instance, I would say 90% of the fires are human caused. Lighting is also an important issue. Sometimes lighting creates larger fires because they occur in remote locations, but fire ignited by humans is also a very important aspect. Not just obviously arsonism, which is there, but mostly accidents. No, I mean fires that tend to manage grass or shrubs, and therefore they escape out of control and became large events. So there is a very wide diversity of factors related to fire, and I think the sociological analysis of fires is also something that has not been previously much.
And that's what your project's changing. You're looking at stuff that goes just beyond the weather conditions, right? Super. Well, thank you for explaining that so clearly. And it sounds very much like your work is needed, because I don't think the situation's going to get better. Thank you. Thomas, turning to you. Fast detection and unequivocal identification of chemical hazards at low concentrations in gas and in liquid phase in multiple environments. The Surfing project has developed a device to help first responders deal with chemical threats. So, Thomas, can you tell us a little bit about surface enhanced Raman spectroscopy? I did it the second time. What is it and how does it work?
Yes. Okay, so maybe it's simply we split sort of service-enhanced Raman spectroscopy in two parts for simplicity. So let's begin with the Raman spectroscopy. So many people have heard this before. So Raman spectroscopy is a well-known, actually, and quite old analytical technique that is essentially used to characterize and identify, like in our case, unknown material, right? That's why it's so useful, say, in forensic science, material science, and basically many disciplines. Now, the way it works is typically you have a laser, you shine a laser, like in our case, some unknown molecules, and then molecules scatter light, and then molecules are a little bit like people in a sense. You know, we have our fingerprints to identify who we are, and molecules have what we call, vibrational spectral fingerprints. This is how we identify the molecule. So, so let's say if I have a pill of aspirin, I can use a Raman spectrometer to tell me that, yes, this is indeed aspirin. I just looked at its spectral fingerprint, and I can confirm this is aspirin. This is not, say, paracetamol or something else. Right, so that's the sort of Raman spectroscopy part. So now imagine we have a slightly more challenging situation. So imagine I have a glass of water, and now I take, from my previous example, just a tiny bit of aspirin, and I add to this glass of water. And as it dissolves in the glass of water, now we have a situation, what we call trace amounts of aspirin. Now, if I take a Raman spectrometer and sort of try to measure it, it will tell me, well, I see water. And I'm like, are you sure? I've just added a tiny amount of aspirin to it. Yeah, I just see water. So you see, this is a limitation of the Raman spectrometer. And this is where surface enhanced part comes in. This is where we use surface, just like in the name, to enhance the Raman signal, sort of boost it many orders of magnitude. This is where we're sort of able to, like, I take like pull away like a curtain, this water aside, and sort of look deep inside, see what else is hiding. And that's the part, surface enhanced Raman spectroscopy. So we're able to find trace amounts of compound.
Yeah, no, that's beautifully explained. Thank you so much. Excellent explanation. Now, how did you feel when you realized how powerfully the boosting factor was and how tiny amounts of trace was actually showing up? It must have been quite exciting when you first realized that.
Yes. It was, we're always very excited to be able to detect as small amounts as possible, even though during the project, we've realized that the real life samples, it's not just like in my example, glass of water plus aspirin. Like typically imagine you have a way more complicated case. Say you have a glass of wine. Okay, now you have so many of different types of molecules in there. And if you're measuring cells, each of them sending their fingerprints. So you're sort of overwhelmed with these fingerprints. Well, now this is where AI comes into arena. This is where we now surprisingly able to train AI to quickly sort these fingerprints and sort of group them together, and we can tell them what we are interested to find, and AI will help us to quickly pinpoint the molecules that we actually want to find.
Fabulous. Brilliant. And I mean, yes, all of this power, but also what I think is thrilling about your project is that you managed to develop a small, lightweight, very compact device that could be held by first responders. So all of this power, but in a compact little device. Can you tell me more about the actual device that the project developed?
Yes. So, handheld Raman spectrometers are actually quite common. So first responders do use them in their everyday work, but not the surface enhanced part. Right? That we added together with the artificial intelligence or deep learning algorithms, so that our tiny sort of prototype had basically, big red button, and the first responder had to just put a sample, press the red button, and then it would analyze, and on the screen you would get sort of an answer. And it was all possible because we had artificial intelligence basically looking like a detective through all these complex matrix, real life samples that have many types of different molecules. So as a detective, it finds what we look for, and then you get the answer on your screen. And we were able to actually shrink it quite significantly, connect it to cloud, and add some more interesting features to it.
And the benefit of collecting it to the cloud was what? So that the data could get back to people who would then be responsible for deciding what to do with the environment in that context.
Yeah, exactly. So imagine you're measuring, say, fluid on a field. Well, then maybe you need experts sitting somewhere else to actually look at the data. Maybe you don't trust completely your AI algorithms yet. Or maybe you say want to measure gas and the way that it's spreading in a field. So maybe you would like a data from sensors in different locations, to come to a centralized place where people could visualize on the map how the cloud is spreading.
Wonderful. Okay. And I know that one of the breakthroughs for you, a major milestone, was the detection of novichok in various mixtures. Yeah. So, for example, can you tell me a little bit more about that? How precisely were you able to measure that?
Yeah, this is an interesting story. Back in 2018, when we sort of wrote this artificial intelligence for spectroscopy, you could hear just whispers. And definitely you couldn't hear much about, warfare. We could only imagine potential terrorist attacks. But then as time progressed, and because of the war in Ukraine, we thought that it would be really relevant to test the technology, put it to a real test. Also, we tried to construct a scenario that someone, wants to poison or add novichok to liquids that people use in everyday lives, say nose spray or mouthwash or anything that you use on every day. And we thought, okay, this would be a good test. We take a novichok, we add to it, and we see. And we were a little bit skeptical. We thought that maybe we were over optimistic, but actually this is where artificial intelligence really surprised us. It was incredibly fast and really better than all previously used methods. So I'm really optimistic about the future. So we're able to detect, for example, novichok in nasal spray several orders of magnitude lower than is possible with conventional Raman spectroscopy.
Right. Excellent. Okay, super. Thank you. Good technology to have. Final question for you, Thomas. Can you see a way that your technology could be used in the future? Are there other developments as AI gets stronger and you bring the two together? What do you see for the future?
Well, I mean, I can't imagine now, AI being outside the picture in spectroscopy because it performs so well. I think we definitely going to see AI entering all types of analytical tools. And Raman spectroscopy and SIRS, definitely. And as Raman field, develops, the tools, interestingly, are getting smaller, cheaper, better. Now we have AI, working for us, this very powerful tool that can analyze the data quickly and help us to sort out all these components, in real life fluids. I think that you will see in the future definitely tools that AI will be embedded in it without any question.
Yeah.
And maybe even inside your mobile one day.
Right. Wow. So ubiquitous. Well, yeah, no, I mean, we have to think blue sky, don't we? Yeah.
Yes.
Excellent. Thank you so much. So basically, the limit is only our imagination. Does anyone have any questions for Thomas? Yes, Patrick, please.
Yeah, actually a comment where this could be very useful. So we actually have a Raman spectrometer on board a rover called the IDEFIX, developed by the CNES and the French Space Agency and the DLR, German Space Agency, that will be on board the MMX mission by the Japanese Space Agency that is going to take a sample of Phobos, one of the moons of Mars, to return it to Earth. And before doing so, they will deploy a rover on the surface of Phobos. The rover will rove very slowly, and it has a Raman spectrometer to do elemental analysis of the surface of Phobos. So this is where I think, your tools could be very powerful.
This is so nice to hear, Patrick. Thank you.
Yeah, you see the reinforcement of the direction you're going in, Thomas. But also, Patrick, it sounds like his equipment is more sophisticated than the usual ones. So you said basic analysis, or, you never know. Thomas might actually be able to help you with something a little bit more than basic. Anyway, this is what's so wonderful about CORDIScovery. It's the synergies. Yes, Emilio, you have a question.
Yeah, well, I have a general comment about the use of artificial intelligence. Sometimes I have the impression that it's being used as a tool to classify data, but sometimes the scientific basis to understand properly the problem is not that clear. What is your impression on that?
Well, I think, Emilio, you are right on the money here. I mean, the algorithms in this project were developed by DTU Compute, so Technical University of Denmark. And actually, you're right. Often when we ask them why the decision in certain cases by AI is made, these researchers actually say, we're not sure. We have to look into it. We have to dig deeper. So actually, you're right. We see that it works, but actually why, in many cases, it's not really clear. Even experts have to, launch special analysis activities to find out why certain decisions were made, why it was classified, as this type, not that type. Because when you look at the spectra, it's not obvious why a decision was made.
Perfect. Like all science, it raises more questions than it answers. On to the next chapter and the next chapter. Okay, listen, thank you so much, the three of you. That was fascinating, and clearly the technological advances you're all coming up with are helping us to remain safer, for which many thanks.
Thank you.
Thank you. Thank you.
Thank you so much, all of you.
Thank you. Bye-bye. Take care.
Bye-bye.
Bye-bye.
Bye-bye. If you've enjoyed this podcast, follow us on Spotify and Apple Podcasts and check out the podcast homepage on the Cordis website. Subscribe to make sure that the hottest research in EU-funded science isn't passing you by. If you've enjoyed it, spread the word. We've talked about how sensors can determine the sex and age of a flying mosquito. In our last 45 episodes, there will be something there to tweak your curiosity. The Cordis website will give you insights into the results of projects funded by the Horizon 2020 and Horizon Europe programs that are working in this area. From motorbikes to motor neurons, there's something there for you. Maybe you're involved in a project or would like to apply for funding. Take a look at what others are doing in your domain. So come and check out the research that's revealing what makes our world tick. We're always happy to hear from you. Drop us a line, editorial@cordis.europa.eu. Until next time.